Welcome back. The COVID-19 pandemic, which is on everybody's mind to some extent. How do we get to this process? How do we get to this analysis that led us to the idea of flattening the curve, especially through processes of social distancing and oftentimes quarantining of ourselves, personal quarantining? As we get further and further into this process, it's going to be more and more difficult, I think challenging, to really live out that idea of reducing or flattening the curve. And I think for engineers, it's really important for us to be able to utilize our understanding of the problem as an engineer would. And this analysis truly is that of a dynamical system. So that an engineer would be able to put together and talk about meaningfully. You can see this flattening of the curve here. Each one of these curves is the percentage of the population that is infected as a function of time, where really we've scaled time here appropriate to the characteristic recovery time in the problem. And what we find out when we do that is that there's really only one dimensionless parameter that things depend on. It's called the R0 value, which has received some popularity in movies and pop culture. I'd like to explain it to you in a way that maybe you can explain it to others and just use your intellect to really look at this situation for what it is, and then to be able to make good, free moral choices based upon that understanding, that knowledge. What we're really trying to do is reduce the maximum number of people that are going to be in the hospital at one time. And what we can see here is that the R0 value really determines that. If the R0 value is high, we get a large percentage of the population that needs hospitalization at the same time, and that really isn't going to be possible. And so what we'd like to do is bring that value down to something more manageable. And that's exactly what this curve is showing. So here we've plotted the peak points for every one of these different pandemic curves, assuming different R0 values. So the R0 value, just to kind of get us going, it's the recovery time, characteristic recovery time over the characteristic time to spread the infection. And so a very large R0 means that the recovery time is long and the infection time, the time required to infect someone, is short, and that leads to a very severe pandemic. An R0 value that's smaller, closer to say 2, what that means is the recovery time is closer to the infection time, and so there's an opportunity for the disease to die out naturally. And what we'd like to do is really reduce this R0 by causing the infection time, the time required for the infection to move through the population, to become longer by separating ourselves from one another. So let's go ahead and kind of do this analysis, but to get there, we've got to go through the process of looking at differdiffential equations and really numerical methods. And so engineering for the common good is what this is all about for me. I hope you can understand the same, that this is your vocation as an engineer. The common good demands that we as engineers understand this model, what gave birth to this result and to the current public health policy that's in place. But it really demands a much bigger picture. It's not enough to just have this picture. We have to understand why we're doing it, and we have to be able to articulate it to other people in a way that's not just winning, it's truthful. And it also, I think, can marry science and faith so that people are able to look at this time through the lens of being able to be closer to Christ, that Christ is present to us in it, and that Jesus really gives us an opportunity here to make a difference to others. And we ought to do that as engineers through our vocation. So let's get started. This is going to take a few videos, so bear with me as we move through the material, but I think you'll find that it's worthwhile. To start with, let's review forward differencing. Forward differencing was the method of computing a derivative based upon discrete data that was given approximating a differential curve. And so the forward difference method was the easiest of the various methods to create this derivative. Basically, it takes the rise over the run between neighboring points to compute the derivative at the initial point. So I look forward to the next point in the series and take the rise over the run between those two data points to compute the derivative there. We saw that this was very easy in MATLAB. We could make a little function to do that. In this case, we're going to be doing something slightly different. What we're going to be doing is really running the forward difference approximation backwards, and we call that Euler's method. What does it mean to run it backwards? Well, in this particular case of using forward difference, we knew the data. Now what we're going to know is the derivative instead. We actually are going to know the derivative, and we'll see why this makes sense in terms of our current situation in a minute. But if we know the derivative, we can solve this forward difference approximation for yi plus 1. And what that allows for us to do is to construct the yi plus 1 data point given the yi data and the derivative there. And if we know the derivative everywhere, then we can definitely compute that derivative at a known value of y. And so this would allow us to jump from one point to the next. So using the data at the previous point to get to the data at the next point. This would allow us to kind of daisy chain our way through the entire data set and reconstruct this curve. This is what's known as a differential equation, or an ODE. And to solve an ODE, we need an initial condition. So we're not really going to talk about how to solve these in terms of a closed form, which you have a whole other set of classes to do. Here we're going to talk about how to do this numerically on the computer, which is actually the way most ODEs are solved. So explicit Euler method, this is exactly what we're going to be working on in this video. In a pandemic, the reason that this Euler method is useful is that what we know is not how many people are going to eventually be infected. That's not actually what we know at first. What we do know is that the mechanism by which people get infected is interactions between the uninfected population X and the infected population Y. We're going to take a very simple model where we're going to say that the product of X and Y times some constant of proportionality gives us that rate of infection. So in this expression here, X and Y are related by an algebraic constraint. In our simple situation here, we're going to say that X and Y both are, all people fall into either one of those two bins, and so the total number in that in the population being a constant, X and Y are related to one another. X plus Y is a constant. In this expression also, we're going to have that the constant of proportionality has to have units of 1 on persons times time, and the reason for that is that the dimensional homogeneity of the rate equation here requires it. On the left-hand side, we're going to have persons on the top, small change in persons, over time in the basement, a small change in time, so this is persons per time. The right-hand side has to have the same units. Since X and Y both have units of persons, alpha has to have units of persons time to the minus 1. We're also given our initial condition, since we have to have that in order to have a place to basically begin constructing our curve. That's going to be our patient's zero, so to speak, the number of people who are initially infected with the disease. So first thing to do is rewrite this differential equation in terms of one variable, and we're going to do that by getting rid of x here in favor of y, since we've got the derivative in terms of y directly. And this is what our ODE now has become. ODE, once again, stands for ordinary differential equation. So it's just an equation that's basically defining a derivative. It's giving what the derivative is equal to. In other words, we start off knowing what the derivatives are given a y value. So the derivative, the fact that we have an infection rate being a function of the number of infected individuals, what that means is the infection rate is not a constant. And so this is one of the things that's oftentimes misunderstood in terms of pop culture. People talk about the R naught value as in terms of some kind of rate. Well, the rate is always changing in any differential equation or system of equations that's describing an epidemic. So it's confusing to people because it's inaccurate to really speak in terms of a constant rate of infection. So we'll see that more and more as we go through. We're going to solve this ordinary differential equation. You could do it analytically. It's a very famous equation known as the logistics equation. But we're going to do it numerically, and since we can do both analytic and numeric solutions, we can compare the two and come up with an error. Solving our difference approximation for y plus 1, we have our Euler's equation, where h here is the step size. It's just the time dt that we're going to look in between steps. So if we go back to our original grid, in between each point on our solution grid, we have a time dt of h. So h is our constant step sizing for this equispaced grid that's going to occur. So if we start this process, it's very simplistic. We start knowing the number of infected at the initial time. So we know y0. We know the derivative at that for that number of people who are being infected, because we know it exactly. It's just alpha times the quantity n minus y0 times y0. That's going to be the infection rate at the initial moment. We take that infection rate, multiply it by the small change in time that we're going to be experiencing to get the next value of the solution. And we end up with y1, the next value of the solution, be equal to the initial value, y0, plus this slope times h. And another way to think of it, this is the slope, which is the rise over the run, times the run. So this is going to give us the small rise between y0 and y1. We add that small rise to y0 to get y1. Once we've got y1, we could do the exact same process over again, except instead of beginning at y0, we now start at our next solution value, y1. And so plugging in for y1, we can get the derivative when the number of infected is y1 being this value. We have our constant time stepping. y1 is known. We can compute y2. We can move through the entire chain of solutions this way. So the first step is just to get a little code working in MATLAB. We're going to do a very simple approach here. Alpha is 0.3, h is 0.1 days, the number of initial infected people is 1. We're going to take a total population of 10, which is just a toy first example. And we've written this down here below in terms of a kind of abstraction. So instead of writing down literally how to get y1 and how to get y2, we're going to start off by getting the next value from the current value, where the current value is going to be in an array with a certain index. So the index 1 is the first value. In MATLAB, we can't start at 0, unfortunately. We're going to start at the first value being 1. So y1 is known. The derivative at y1 is given right here, all of this. H is known. We go ahead and compute yi plus 1, where if I is 1, that's going to be y2. So that allows us to compute y2. And next we're going to compute y3 from y2 and so forth. So you can see that each one of these lines has the exact same equation in it. The only thing that's changing is the index I. This is set up for a for loop. And so what I'd like you to do is kind of stop the video at this point, go ahead and put this into MATLAB and compute y2. You can either compute it directly, explicitly, or use a for loop. It doesn't matter. Compute y2. It should be about 1.27 on persons. Go ahead. So here's the file that is able to generate this integration. We can go through it step by step. We initialize the MATLAB workspace. We set up our parameters, the number of people in our population, alpha. Our initial time is 0. We're going to integrate up to 3 days. We're going to look at an initial patient 0 number of just one person. This one line here, line 6, f, is a function of y. And f here is just our shorthand for the derivative, which is what we know at every time step, given the value of the number of infected persons. Our step size here is 0.1 days. We go ahead and set up the number of panels and the number of time steps in total, including the first. We initialize our arrays, setting up our initial condition here, and then we go through the loop. So after every step, we find the new time by taking the old time and adding h to it. And then we find the new value of the number of infected individuals by taking the older value plus h times the derivative at that older value of infected individuals. After that, we're able to actually compute the exact solution for this particular differential equation. So the exact solution can be found using a method of partial fractions. I don't expect you to be able to do this, but it might be interesting background knowledge to give you this exact solution right here, which is this start expression. We have that here on line 16, and what that allows for us to do is really compute an error. The L2 error norm is really the traditional error norm used by most computational scientists. And the way that we do that is we're basically computing the square root of the integral under the curve of the error squared. And so what that looks like when we write it in terms of MATLAB, basically this should look kind of like what's inside here, inside the square root, should look like the rectangle rule for you, because it actually is just computing this integral using the rectangle rule. So EI here represents the error at every point in the grid, and we're going to have error at every point because each point is got to have a numerical approximation for yi that came from the derivative, but it's not going to be exact. And so in this particular case, we have the exact solution, which is unusual. Normally, if we have the exact solution, we'd have no reason to do the numerical integration. But in this case, it's helpful because it allows us to go ahead and compute an error norm. We go ahead and do that on line 18 here. the L2 error norm is computed just really using these indices to take the points of interest for each panel in terms of the error, squaring it, summing it up, multiplying it by the step size, which is a constant for each panel, and then taking the square root to give us the L2 norm of the error. We would find that that L2 norm of the error would decrease as h goes down, as the step size goes down. So here I've gone ahead and printed out the values for the time, the number of infected persons, and the exact number. And you can see that we're pretty close for a step size of 0.1, but there is some error, there's some discrepancy, even after the first time step. So that is how we would approach the problem. Let's kind of make this real by getting a real alpha for a real population. So the easiest way to do that would be to go to get the COVID-19 data that's being put together for us by the Johns Hopkins University. Go ahead and just Google GitHub COVID-19 data. Click on the first link to go to their GitHub. And then once you're there, you're going to click on CSSE COVID-19 data, then go to the time series data, click on that, then go get the confirmed data, and then what you're going to want to do is click on raw, and what that will do is give you out a raw data file that you can then save directly in your web browser onto your computer into the file where you've written your code, and then you can load that data directly into MATLAB using the import data command, which is quite handy. So import data, when you do this line 2, import data is going to not just import the numbers, it'll also import all of the various headings. And so we just want the numerical values. The way we do get that, reduce the data down to just the numerical values, is we take data.data and set that to equal to data. After line 3, data just has the numerical values in it. First thing I did was grab off the GPS coordinates of line 157, which is what South Korea's GPS latitude and longitude should be. You might want to check out that that's the case. The reason we're going to look at South Korean data is that they did a very good job of controlling the outbreak, and they're actually on the other side of the curve. So they have a kind of complete data set for us to look at. We go ahead and grab the rest of their line 3 through the end, and that's the number of infected persons confirmed as a function of the days, the number of days, one for each day. We're going to assume that the total population that's ever going to get infected is about 1.1 times the last value in their data set. The number of data points is just the number of days that we have data for, and we set up a time array that goes from 0 times 0 all the way up to the number of data points minus 1. And we go ahead and plot that data. And so you'd plot that data here in the first line. You got the number of days on the x-axis and the number of infected people on the y-axis. And then what I've done down here is kind of interesting. I've taken the forward difference of this data and plotted the derivative, dy dt, but I haven't plotted it as a function of time. Instead, I've plotted it as a function of y, the number of people infected. And the reason for that is that we should expect that dy dt is a function of y. In fact, if we go ahead and expand this, it would be alpha times n times y minus alpha y squared. So this minus alpha y squared, what that means is that we should expect this to be an upside down parabola, something that's got a y squared as the highest. And indeed, if we look at this kind of looks like a parabola, not exactly, it's data. And so what we're going to do is try and find the alpha given this derivative data. And the way that we do that is we take the derivative that we've just computed, we take the value of y that we know, that we've just plotted, and we go ahead and just take n minus y times y and divide y prime for it. For each data point, that gives us an alpha. That's kind of nice because now we have an alpha, but we're going to have a different alpha for every data point in the set. If things truly fit an upside down parabola, we'd be giving only one alpha, but because it's real data, there's a lot of variation. So we just take the mean of all those and call that good. And the alpha that I found was about 2.4 times 10 to the minus fifth, 1 on person's days. And that's an interesting unit, as we've already noted. So to get the derivative here at each point, since we would like the derivative of each point, what I've done is come up with a little baby function called d1, which actually uses the forward difference at the first point, the central difference everywhere else except for the last point where we use the backward difference. And what that allows for is for me to get an actual derivative for every data point and not have to omit any of the data points when we're trying to compute alpha here. And so that's what I've done here on line 16, used D1, which kind of puts together the forward, central, and backward differencing all together. Computed the alphas for every point using the dot operator, taking the mean value of it, and then going ahead and plotting that here. And you can see that things are kind of off. This is the actual value of y prime as a function of y using our given the value of alpha that we just found. The reason that we're off is because between 0 and about day 25, there really wasn't community spread in South Korea. Around day 25, something happened. I believe a church met, and accidentally community spread began. So really there's a whole different kind of epidemic modeling that ought to be used earlier on, and it's all of those points which are actually causing a kind of all those points have a different alpha. It's causing this value to be skewed over, like we're seeing there. So if we use that value of alpha and we go ahead and actually run through our code with that value of alpha and with the number of persons being 1.1 times the final number of people that was infected on whatever this last day was that I downloaded the data, what you'd see is that we'd get this very nice exact and differential numerical differential approximation, really lining up well with the data here in terms of how this epidemic is really carrying itself forward into time. So that's a pretty powerful little example of how we've actually gotten some meaningful kind of behavior out of this model. But I think a better question might really be, what is alpha? That was really the hard part. We needed to get alpha in order to get this problem working, including, as well as we needed to get a value for the number of persons in the population. But what does that really give us? And so let's talk about alpha from the point of view of what it physically means. If we take a look at the differential equation, we can see that this differential equation here, the rate of infection increase, is really due to what we might call interaction, or what some scientists have been calling community spread. What this means is that the infected and the non-infected people coming into contact with each other is what's actually causing the infection to spread, and what's describing that is alpha. But it has really weird units, and it'd be nice to try and get a number that makes some sense in terms of a physical mechanism. So to get this kind of meaningful understanding of alpha, we really need to scale our problem. And so bear with me, this is a new technique, but it's something that we're going to be using even in our project. So we have our initial condition and our differential equation, and in this two guys, we've only got two parameters, alpha and n, and y naught, so excuse me, three parameters, but there's only two variables, y and t. And so when we scale, we're going to scale the two variables, as indicated by the derivative here, y and t. We want to scale them so that what comes out is ultimately a percentage. So if I take y, for instance, and divide it by the total number of people in the population, I'm going to get the percentage of the population that is infected. So y star here represents this dimensionless ratio or percentage. So whenever we see a star, we should think of a ratio, and it is dimensionless indeed. If y has units of persons and n has units of persons, y on n has no units, so it is dimensionless. Similarly, t star is going to be a dimensionless percentage or ratio, t on tc, where tc here is going to be a characteristic time for our particular problem. But what we'd like to do is allow the problem to tell us what tc is. And in fact, we'd like to know tc in terms of our other parameters. So tc is a constant characteristic time that's really going to be determined by our problem once we make a substitution for y and t in terms of y star and t star are scaled percentages. So let's go ahead and do that. Wherever there's a y or a t in our differential equation or in our initial condition, we're going to substitute for what that is in terms of y star and t star. So y is n times y star. That's what y is. It's n times y star. So wherever there's a y, I'm just going to put in n y star. So dy becomes now d of ny star. over here, this y becomes ny star. This y becomes ny star. This y here becomes ny star, for instance. Similarly, t, wherever there's a t, I'm going to replace t by what it is in terms of t star. What is t? T is tc times t star. So wherever I have a t now, I'm going to place tc times t star. Tc times t star. And so now what we want to do is, the problem yet isn't dimensionless, but what we can do is start the process of rendering it dimensionless by getting rid of these parameters and putting them together. So what we're going to do is, you can see n times y star equals y naught. If we were to divide through by n, we're going to get that y star at, well, take a look, t star times tc. If I divide both sides of this equation in the basement here by tc, 0 on tc, whatever tc is, that's still 0. So in other words, when t is 0, t star has to be 0. So y star at t star equals to 0 is now going to be dividing through by n on both sides, y naught on n. This is a dimensionless percentage. In fact, it's the initial percentage of the population that is infected, the patient's zero, so to speak, percentage. We should expect that to be a pretty small number in comparison to the total number of people in the population, so we're going to call it epsilon. And this is our first dimensionless initial condition. It's our first dimensionless equation, really. Over here, things still had dimensions of population on both sides. Now we have y star, it has no units. At t star equals to 0 is equal to this epsilon, which is the percentage of the population initially infected. So everything is dimensionless now, and we have this dimensionless parameter as well. So the reason that we did that was to render this dimensionless. If we pull out the n and tc from the derivative, because n is a constant and tc is a constant, pull them out, even though tc is not yet known, we know it's a constant. And we rewrite this side of the equation as just alpha n squared minus times quantity 1 minus y star times y star. And then we go ahead and this guy sitting out in front of dy star dt star is a constant with units of population per time. So this is dimensionless. This is where all the units are. Let's render it dimensionless again by multiplying through by tc on n. If I multiply by tc on n here, this goes away, and this side of the equation is going to reduce down to alpha times n times quantity 1 minus y star times tc. Rearranging this one more time, we end up with our blue equation here, dy star dt star equals alpha ntc times the quantity 1 minus y star times y star. And if we look at this expression, we have a dimensionless ratio over here that is really talking about the rate of infection increase. And on this side of the equation, we still have something that's describing interaction or community spread, but it's now in a dimensionless, it's been rendered dimensionless, where there's only this single constant sitting out in front. Now, the way to view this constant is as if it's a weighting on the right-hand side. It's a weighting, in fact, on the interaction mechanism or community spread mechanism. And over here, we've got our rate of infection increase, and what's sitting out in front of it is an invisible 1. In other words, on this side of the equation, things are what we might call order 1, or weighted by 1. Everything is in terms of 1, or 100%, so to speak. This side is weighted 100%. We'd like the two to be weighted equivalently. We'd like to see the infection spread increase as a result of this mechanism of interaction. And so we're going to make this weighting also 1. We are free to do that because TC has not been picked yet. All we've said is that TC is going to be a constant that characterizes our particular problem in terms of, well, in this case, we're choosing to make the interaction mechanism the same order of magnitude as the rate of increase of the number of infected people. So that means that our domain of interest is really to see the effect of this interaction mechanism by setting the weighting in front of that term representing that mechanism to be equal to the same thing as dy star dt star, a 1. Solving this guy for TC, we get that TC is equal to 1 on alpha n. And that's our big takeaway right now. The characteristic time that allows for the interaction mechanism to really be visible and allow for it to be weighted the same as our rate of infection increase would be to set that characteristic time to be 1 on alpha n. So 1 on alpha n is in fact the characteristic time for community spread. And that's really what alpha is. Alpha is the thing that when I multiply it by n and take 1 on that value, I get the characteristic time to see community spread in our problem. And that's pretty powerful, because that gives us an expression that really gives meaning to what alpha is. And of course, alpha times n has units of seconds or time. So now look at what our differential equation has become. It's completely dimensionless. Both sides of the equation only involve starred quantities which have no units. And it's very simple. All of the extra bits alpha n and y naught have gone away, and we're left with just one parameter remaining, epsilon. So the initial percentage of the population that was infected is what's going to determine how our solution behaves. If we wanted to go ahead and kind of analyze this a little bit, when will y star prime, or dy star dt star, when will that be equal to 0? And you can see that that's equal to 0. This side is already factored when either y star is 0 or when y star is 1. So if initially there's no people infected, then there's never going to be any spread. Dy star dt star is 0. Or if all the people are infected, so when y star is 1, what does it mean when y star is 1? It means that 100% of n is y. In other words, the whole population now has been infected. Y is equal to n. And that's the other period, or the point at which the differential equation peters out and there's no longer any rate of infection increase. So if we were to plot this guy, dy star dt star, or y prime, as a function of y star, we would get this upside down parabola that's going to basically peak out when y star is equal to a half. And when y star is equal to a half, dy star dt star is equal to a quarter. So what does a quarter dy star dt star mean? Well, dy dt up here, that's just going to be equal to n over tc times dy star dt star. Well, dy star dt star is a quarter. And so I'm going to end up with tc here being alpha n. This is just going to turn into a quarter alpha times n squared. And so this is the maximum, this is the peak of the rate of infection spread. And that's what that number would be, and we can get that really without even solving the differential equation. So there's a lot of value in this scaling process for giving physical meaning to the parameters in our problem, not just a kind of weird knob that we tune, so to speak, arbitrarily to get it to fit data, but it gives us some meaningful expression that gives us an ability to physically characterize what alpha is really telling me. And then on top of it, we're able to kind of see this universal scaled solution, which is very simple, where there's only one parameter remaining, so there's not alpha n and y naught anymore, there's only epsilon. And lastly, this is a universal expression, which means that it would be appropriate for any kind of physical situation that when I scale it reduces down to this pure mathematical form. And so that's what we mean by a universal ODE. It's really not any longer strictly related to simply epidemics. And in fact, the logistics equation is got many different applications, but one of them is, at least primarily at first blush, a kind of way to model epidemics. So we can go ahead and scale all of our data. So TC is just 1 on alpha NP. We can go ahead and scale our t values by tc, our y values by np, scale yp by tc on np, and plot these guys. And so now we have our scaled dimensionless plot. So this dimensionless dy star dt star plot as a function of y star is exactly what we would have seen over here, only it's now rendered dimensionless. And in our particular problem, if we take alpha on n, alpha times n 1 on that, we're going to get 4.5 days is about the amount of time we need to watch our situation in order to see the effect of community spread. In our problem, it's really interesting to note, as I said, that on about day 25, a second kind of round of infections began with a different kind of dynamic. And so if you were to retool our data here by taking, instead of all the data, just day 24 and up, and then also change the number of persons that we're going to be considering that are going to be totally infected into the last value times 1.02, slightly larger than the last value, you're going to get a different value for our behavior, and TC will drop. So now it takes much less time, only about 3 days, whereas before it was taking over 4 days to see the effect of community spread. And so this really indicates that changing our behavior changes alpha, which changes TC. And if we want to make the amount of time needed to spread the infection go up, we got to behave in such a way that it really allows for that to occur. So in our next video, we're really going to focus on the next form of the system of differential equations that could be used to model our epidemic, and it's called the SIR model. So next time we'll get to R naught and into a slightly more exciting system of differential equations.